Bismillahirrahmanirrahim. Assalamu alaikum. In the previous video, we gave you an introduction to unsupervised learning and clustering. We also studied different aspects of clustering, including the notion of similarity, how do we evaluate the performance of clustering, and what are the clustering algorithms we have in the literature. In this video, we will talk about partitional clustering techniques with a focus on K-means clustering algorithm. In partial clustering, we have a data set D of n points where each data point is in the D-dimensional real space. Partitional clustering constructs a partition of n data points into a set of k clusters such that partitioning criterion is optimized. This criterion could be that we should have more compact clusters, or we should have interseparability of clusters is maximized. So we could have different partitioning criterion, and we can use this clustering to carry out partitioning of the data in the feature space. So we note that we have disjoint clusters. It means each data point is a part of only one cluster. Finding globally optimal clustering would require exhaustive search over all the points and partitions, and therefore we use heuristic algorithms for clustering, and these heuristic algorithms found to be more effective. And for example, K-means or K-medoids are the algorithms which are very frequently used in the literature to carry out this partition clustering. So what is K-means? Each cluster is characterized by the center of the cluster. But center of a cluster does not need to be a data point. Instead, in K-medoids, each cluster is characterized by one data point, which we call medoid, in the cluster, for which the average dissimilarity to all other data points in the cluster is minimal. Right? So this is the main difference between K-means and K-medoids. In K-means, we maximize separability. We try to have more and more compact cluster, but the centroid that characterizes the cluster does not need to be a data point. But in K-medoids, we should have a data point which is which characterizes the cluster. Right. Let's start with K-means algorithm. In Kmeans algorithm, we partition the data D into K cluster. We assume that the K is given by the user. That it means we know the number of clusters in the data. So each cluster is a group of points, and let the clusters be denoted by C1, C2, Ck. We have K number of clusters, and each cluster is characterized by its center, which we refer to as cluster centroid, or centroid for short. It's also known as the mean of the center, or the center of the gravity of the cluster. Right? So mathematically, we can define the centroid as a mean of the points in the cluster. So we denoted with mean with this symbol mu. So for cluster Ci, we define its centroid as an average of all the points inside the cluster. So we are simply taking a summation of all the points in the cluster, all Xj data points, and we divide by total number of points in the cluster Ci. This is a mean of all the points. So this is a centroid of a cluster. Okay. So we are all set to define K-means algorithm. So in K-means algorithm, we carry out the following steps. So input is data set D and the number of clusters, this variable K that is defining the number of clusters. So in algorithm, we randomly choose K clusters. So we initialize algorithm by randomly choosing K points in the feature space. Okay. So we choose K centroids in RD randomly. And after this initialization, we iteratively run an algorithm until convergence. So we iteratively run these two steps. First of all, each data point is assigned membership of the cluster of closest centroid. So we initialize centroids. So each centroid characterizes a cluster. Now we need to assign membership of each data point to the cluster, right? So we need to define this association between data point and cluster. For each data point, we assign the membership of the cluster to this data point. Uh, uh, so this data point is given the membership of the closest centroid. So once all the data points are given membership of the closest centroids, we compute the centroids again for each cluster using the current class memberships. And we keep on doing until the convergence is achieved. I will define very shortly what do we mean by convergence here. Okay, what are the computations involved here in these steps? And what is the complexity of the algorithm? These computations involve, we randomly choose centroids, mu for each cluster CI, and we repeat until convergence. The first step is for each data point xj, we assign the cluster CI such that distance between xj and cluster centroid mu CI is minimized. Right? So this point xj is closer to CI, closer to mu CI than all other centroids. And therefore, we assign the cluster CI to xj. And we do this for each data point. What's the complexity of this? We are computing distance. Okay, for one data point, we're computing this distance, and we're computing distance from every centroid. So complexity to compute distance is d, because we are in d-dimensional space. We have k such clusters. So k times d would be assigning membership to one data point. And if we have n data points in total, the complexity would be of the order number of clusters times number of data points times the size of the feature space. In practice, the number of clusters is small, and number of feature space is also small, and therefore we often term that the complexity of K-means algorithm is linear in terms of number of points. This is linear function of n if we assume k and d are small, right? And then we recompute the centroids as follows. We simply use the formula which we defined earlier for centroid. So we recompute the centroid for each cluster. Right? So this is a K-means algorithm. It's super simple. It's computationally efficient. As I said earlier, it's linear with the number of data points. What's the complexity of this second step? N times d, right? Because we are simply computing summation of all data points, and we have each point in the d-dimensional feature space, so it is nd. So overall complexity is order k and d, and this is linear with n if we assume k and d are much smaller than n. Right. Let me illustrate this with the help of one visualization, with the help of one example, and this K-means algorithm. Okay, we assume that we have these data points, so these blue points, and we randomly initialize cluster heads. Right? So here k is equal to 3. So we assume that k is equal to 3 is given, and we have this data set. So these points are D. So we randomly initialize cluster heads. Right? So we say we have 3 clusters. We want to group these data points into 3 clusters: red, green, and blue. Right? When they're randomly initialized, I get these cluster heads: red cluster head, green cluster head, and this is a blue cluster head. Now I'm going to iteratively carry out 2 steps. The first step is, so I will be assigning each point to the closest cluster head. And this assignment would give me this. So all of these red points are closest to the red cluster head. The blue points are closer to the blue cluster head, and only these points are closest to the green cluster head. What's the next step? We update cluster heads. What do you expect? So this red cluster head would move somewhere here, because this is the center of all the points, mean of all the points. Similarly, we expect this blue point to move towards inside slightly, right? So that it's a true center. It's a true centroid of all the blue points. It's the mean of all the blue points. Right? So when I recompute, when I update cluster heads, I get these as expected. What's the next step? So we assign each point to closest cluster head. You see these red points. So okay, these red points. So these red points are closer to green than red. So these must be assigned a green label. These must be assigned to green centroid. When we do reassignment, we get this. Next step, we update cluster heads. The red would shift further towards left, and green, we expect green point to move up. That is, and if we again do reassignment, we obtain this. And once we readjust cluster heads, the green would stay almost the same place. The blue has almost converged, but the red will be shifted towards left here. So now at this stage, we can say the algorithm has converged, because if I carry out further iteration, so the reassignment won't happen, the cluster heads won't change, or the size of cluster is not going to change. So this is, we can say, the algorithm has converged. Yeah. So from here, we can also reduce convergence criteria for K-means algorithm. We can define multiple convergence criteria. A simple could be the convergence of the reassignment data points to different clusters. It means the reassignment is stopped or minimized. So each point is getting the same cluster centroid in every iteration. You can say reassignment has converged, or location of centroids has converged. So we note if the points are not being reassigned, the cluster would stay at the same point, right? Or we can say we can use convergence of the sum of squared error, which is defined as this. Okay, let me explain this. So distance of xj mu ci. So this explains the distance between a data point xj and a cluster head mu ci. And we are taking point xj from the cluster ci. Right? So this quantity distance would give us the distance of every point in the cluster to the centroid of the cluster. And when you square it and we sum over, my apologies, and we sum over all the clusters, so what we get is a measure of spread of the points around each centroid of the cluster. So once the reassignment is stopped when the location of centroid is not updated, SSE would also converge to some value. So it converges to the minimum value. So interpretation is, so any of these three criteria, we can say that clusters are no more changing, right? So the centroids are fixed, no reassignment, SSE has stopped decreasing, right? There should be a remark here. Algorithm may converge at a local optimum. So there's a possibility, and we will see very shortly what we mean by this sub-optimal clustering. Before we look at some issues with K-means clustering, we can talk about how do we evaluate K-means clustering. We can use the same squared error, sum of squared error, to evaluate the clustering performance. Right? This is what we just defined. And obviously, a better clustering algorithm will have smallest sum of squared error. SSE can be reduced by increasing the number of clusters K. If you increase the number of clusters, so we would have multiple centroids in the data, and the spread around each centroid is expected to reduce. Right? Okay. What is the impact of choosing initial centroids? So in Kmeans algorithm, we choose centroids initially randomly in the feature space. There's a possibility that the choice of initial centroids is such that we have suboptimal clustering instead of optimal clustering. Okay, let me illustrate this. Right. So with choice of initial centroids can significantly impact the performance of the clustering. We can have slow convergence rate, or there's a possibility the algorithm converges to suboptimal clustering. Okay, consider an example that we have these original points. Optimal clustering would yield these three centroids: this centroid, this centroid, and this centroid. So there's a possibility that algorithm converges to suboptimal clustering like this. So if you see, this is a centroid, this is centroid. So algorithm has converged. So if you run algorithm for more iterations, centroids won't change, reassignment won't happen, SSE won't decrease. But algorithm has converged to suboptimal clustering. The possible solutions to avoid this, to handle this, include we carry out multiple runs of centroids and evaluate the performance. It often helps, but the probability that it would help is very low, because you are choosing K centroids in a higher dimensional space, and the probability that you will get centroids at the desired locations, so that your algorithm converges to the global optimum. Alternatively, you can start with more than K centroids and select K most widely spread. So in this case, if you would start with say 10 centroids, we could have small clusters, and then we could pick the 10, when the algorithm converges, we pick the best three widely separated centroids, and we rerun the K-means algorithm on those three widely spread centroids. We can also determine initial centroids using hierarchical clustering, which we will study in the next video. The next topic is hierarchical clustering. So we can run hierarchical clustering to determine initial centroids, and we can use this initial centroids for K-means. We can also carry out some post-processing to handle this problem. So this includes we drop small clusters. For example, in this case, right? So if you drop a small clusters, so and you rerun the algorithm, you can correct this problem. Alternatively, you split clusters with large SSE. So in this example, for this cluster, you have a very large SSE. If you split this into two clusters, so you could solve this problem. You can merge clusters with low SSE. So it should be, for example, in these two clusters here, we could merge these two clusters, and we could form a single cluster by merging these two clusters. Right? So these are the possible solutions which we can employ to handle the issue of suboptimal clustering due to poor choice of initial centroids. In K-means, we assume that we know the number of clusters. So we start with an assumption that we have information about the number of clusters. But how do we determine K when we do not have information about the number of clusters? And that is often the case in practice because we don't know the number of clusters in the data. So how do we address this question, or how do we determine K? The answer is we don't know, but we can use some heuristics to determine the number of clusters or the optimal number of clusters K. So one solution is which is known as Albo method, or it's also termed as knee method, but we will stick to we'll call it Albo method, and that can help us in approximating a good choice of K. Okay, what is this method? In this method, we evaluate the performance of clustering for different values of K. For example, we use SSE as a performance metric, sum of squared error, and we plot it versus K. We run clustering algorithm, K-means algorithm for different values of K, and we obtain SSE for each value of K. And usually we get this plot. We do not get this nice smooth curve in practice, but we often get this and this decaying curve, and eventually it saturates at, for some value of K. So if the plot is like an arm, right, the plot like an arm, right, something like this, the elbow, around the elbow is the optimal value of K. So here you can say either 5 or 6 is the optimal choice of K. Okay. So this is the elbow method. So you plot SSE, you plot the error, your metric of performance versus K, and when we see that after some value of K, we do not get a significant increase in the performance or significant decrease in the error, and that is the good choice of K. So there is another method, in fact, similar to this, that we plot Silhouette coefficient versus K and use this plot to judge the value of K. Again, we look at the plot, and looking at the plot will gives us the optimal value of K. And we will not explore this further here, but this is very similar to the elbow method. Some of the limitations and weaknesses of K-means. We have seen one earlier, that K-means is sensitive to noise, sensitive to initial values of centroids. If you do not choose, if there's a possibility that for some values of centroids, we can have suboptimal clustering. K-means is sensitive to difference in sizes, densities, and shapes of clusters. Okay, let me explain this. Assume that we have these three we have data which is for 3 classes, and if you see for each class we have a data we have different number of data points in each class. So the blue is a smaller size than compared to red, and green is the smallest one. We can say we have clusters of different sizes. When you run k-means on this data, so k-means won't have information about the true labels. When we run k-means on this, we get these three different clusters. Right? So we have too much impurity, right? If we use a purity metric. So, or we can say we have a suboptimal clustering. And this suboptimal clustering is due to the difference in sizes of the clusters. See, take another case. We have different densities of clusters, right? So blue and green are a dense clusters as compared to red. And when we run k-means for k is equal to 3, we know k is equal to 3. When we run k-means on this data, we get these clusters. Again, we have suboptimal clustering. Another example could be when we have clusters of different shapes, or the clusters are not like blobs, or they are non-globular shapes. So in this case, we also have suboptimal clustering because k-means assumes that we have clusters of globular shapes or blobs in higher dimension space. So these are some of the limitations or weaknesses of k-means. So these three cases can be handled with one simple solution, and that is if you start with more number of clusters. Right? Say if you run this for say k is equal to 10, for example. So there's a possibility that you will have a small clusters. So here, centroids here. Right? So you will have similarly for this different sizes case, if you use say k is equal to 6, you will have small centroids. So using a higher value of k or using a large number of clusters can help us resolving these issues to an extent. So that's all for the k-means algorithm. We can look at the summary. And despite these limitations, k-means is still the most popular and fundamental unsupervised clustering algorithm because it is simple. It's a simple two-step iterative process. It's easy to understand. And it's easy to implement. It is computationally efficient. We have seen that the time complexity is number of clusters times number of data points times size of or dimension of the feature space. And usually we have small values of k and d are much smaller than n, and therefore we say k-means is linear in terms of data points. It has a limitation that it assumes that the number of clusters is known. Most of the convergence takes place in the first few iterations. The algorithm converges very quickly, and the reassignment has minimized or the centroid position. The change in centroid position is stopped in the very few iterations. The performance of clustering algorithm is often hard to evaluate, and that is true for every clustering algorithm, in fact. But we can use SSE as a performance metric to evaluate the performance of clustering algorithm. It is sensitive to initial values of centroids. It is sensitive to outliers and difference in sizes, densities, and shapes of clusters. If you have non-convex shapes of clusters, if you have non-globular shapes of clusters, you can have suboptimal clustering for k-means. Right? So that's all for partitional clustering and k-means clustering. So in the next video, we will talk about hierarchical clustering and we will focus on agglomerative clustering. We'll stop here and we'll continue in the next video, inshallah. Allah Hafiz.